Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can divide rational expressions and how we can model in mathematics. So what it means when we talk about modeling is we're referring to doing a word problem related to the more abstract concept that we're practicing. So in this case, we're going to have a word problem related to dividing rational expressions. So let's take a look at how we divide rational expressions. Now, before you watch this video, if you have not already learned about how to multiply rational expressions, you are going to want to learn how to do that first because dividing and multiplying are very similar. So when it comes to dividing rational expressions, what you're going to do is remember a rational expression is just a fraction. And so how do we divide fractions? Well, if I have something like 3/4 divided by 1/2, we all learned at some point in our lives that dividing by a fraction is the same as multiplying by its reciprocal. So sometimes people would learn different phrases like keep, change, flip the action, flip the fraction, different things like that that would tell us how we can end up dividing these fractions here. So if I had something like 3/4 divided by 1/2, I would keep the first, change the sign, and flip the other fraction. And so 3/4 divided by 1/2 is the same as 3/4 times 2/1, or 6/4, which is the same as 1.5. Okay, so there's lots of ways that we can do that. When it comes to rational expressions, because rational expressions are just fractions with variables in them, what we're going to do is we are going to follow the same rules that we do when we are just dividing fractions. So in this case, when we're dividing these two rational expressions, we're going to follow that same rule. Keep, change, flip the action, flip the fraction, whichever one you like. So that means the first one stays the same, 8x cubed y over 2xy squared. We're going to flip our sign, so now we're going to multiply these two and flip our fraction over, 4y over 7x to the 4th, y to the 3rd. Then we can follow through just like we were when we were multiplying. So we can factor, then we can multiply, then we can practice our canceling. And remember that cancel doesn't actually mean that we're getting rid of it. It means that those two things simplify down to 1, and anything times 1 is itself. And then we write that simplified version. So let's take a look at what this is going to end up being. So let's go through those steps. So we want to factor this. So this will factor into 2 times 2 times 2, this one on the top here, times x times x times x times y. And then when I'm going to do this multiply and factor step together. Then this top piece will also be on the top, multiplied by, and we've got a 2 times a 2 and our y. Then on the bottom here, we've got our 2xy squared, which factors into 2 times x times y times y. And that's going to be times our bottom here, which is 7 times x times x times x times x times y times y times y. Poof. Okay, so then what we can do is we can simplify or cancel out what's in common on top and bottom. So we've got a 2 here, I've got an x, I've got a y, I've got another y, I've got a couple more x's, and I think that's everything. So then what we end up doing is we end up multiplying what we have here and writing that simplified version. So I've got 2 times 2 times 2 times 2. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. And that's the only thing on top. On the bottom, I've got a 7 x squared y cubed. So you can see how whenever we're dividing these rational expressions, what we do is we flip the action, flip the fraction, change it from a division problem to a multiplication problem by flipping our rational expression into its reciprocal. So let's take a look at 2 more examples in which we do something similar, and then we will talk about a word problem related. So this next one, we want to divide the rational expression. We're going to do the exact same thing that we were doing before, where we rewrite it. So 7x over 2x minus 10 times, so remember, flip our action, flip our fraction, x squared minus 11x plus 30 over x squared minus 6x. Then we need a factor. And so we're going to factor everything. So this top piece will factor into a 7 over x. This x squared minus 11x plus 30, we can factor using our x method. So 2 numbers that multiply to 30 and add to negative 11. Well, that's going to be negative 6 and negative 5. So we have an x minus 5 and an x minus 6. And then on the bottom here, we'll factor out this piece. 2 is our greatest common factor. So we've got 2 times x minus 5. And here I can factor an x out of that and get times x minus 6. So then what we want to do is we want to simplify and cancel out all those things. that are the same on top and bottom, so we can simplify this x minus 5, cancel out our x minus 6's, and what are we left with? Well, none other than we're left with simply 7/2. Wow, I never would have guessed that 7x divided by 2x minus 10, or 7x over 2x minus 10 divided by x squared minus 6x over x squared minus 11x plus 30 would simplify into 7/2. Simple as that. Now, what do you think would happen if we were dividing by just a constant term then? So in this case, we've got 6x squared plus x minus 15 over 4x squared divided by 3x squared plus 5x. So what does this mean? Well, remember, we can write anything as a fraction by putting it over 1. So all of a sudden we have our fractions here and we can do exactly what we were doing before. Flip the sign, flip the fraction. So now we're at a 6x squared plus x minus 15 over 4x squared times 1 over 3x squared plus 5x. Now that we've split that up, we can then go through with our multiplying process here. So we are going to want to multiply these two things together. 6x squared plus x minus 15. We're going to use our x method to factor that. Remember, when we use our x method, we are going to have to multiply across. And so we're going to have to do that 6 times 15. And 6 times 15 is going to be 90. So we're looking for two numbers that multiply to negative 90 and add to 1. And that's actually going to be a negative 9 and a 10. But remember, because we multiplied by that 6, we have to divide both sides by 6. And so 10 over 6 simplifies into 5/3. Negative 9 over 6 simplifies into negative 3/2. And so what that means is this top piece actually factors into, remember, bottoms up, 2x minus 3. And that other piece factors into a 3x plus 5. And then we just have a 1 on top. And then on the bottom, we've got a 4 times x times, now this will factor into, we can pull an x there, so an x times a 3x plus 5, like this. So times x times 3x plus 5. And then we want to simplify that. We can cancel out or simplify that 3x plus 5 into a 1. And so then we're left with the expression 2x minus 3 over 4x to the third. And we cannot simplify that 2 and that 4 because that 2 is attached to the x, which is attached to the 3. So notice how up above in the step before when we were canceling, that 2x minus 3 was in parentheses. So it can only cancel out or simplify with anything else that looks the same as it. Because this doesn't have anything that's the same as that, we cannot simplify anything else, and that is our simplest answer. So that's how we divide rational expressions. Now, we're going to do one last problem here in which we're talking about how we can apply this idea in the real world. So here's a question. It says the total amount in millions of dollars of healthcare expenditures and the residential population in the United States can be modeled by the two following expressions. I is 171,000 T plus 1,361,000 over 1 plus 18 thousandths T, and P is expressed as being 2 and 96 hundredths times T plus 278.649 thousandths and 649 thousandths, right? So where T represents the number of years since 2000, what we want to do is find a model for M. So when they're talking about finding a model for M, that means we want to write an expression or an equation. So that equation is where we set it equal to something. So where we say M equals, we want to write an equation for this that models the annual healthcare expenditures per resident. So this word per here is a huge clue for us, meaning that I want to divide. I want to take the total expenditures that we have, that I, and divide it by the resident population. Because they're both in millions, we want to make sure that we are keeping that in mind as we're doing our calculations here. So we want to figure out what is this model going to be and then use that model to estimate the annual healthcare expenditures per person in 2010. So let's go ahead and write down that model. So our model, if you think of it this way, I want to figure out the healthcare expenditures per resident. So am I going to take the number of residents and divide it by the healthcare expenditures? No, because that would be the amount of money the amount of residents per dollar. But instead, we're going to do it the other way. We're going to take the amount of income that we get in healthcare expenditures, so that 171,000 T plus 1,361,000 divided by 1 plus 18,000 T. And we want to divide that, because we're taking the total amount of income and divide it by the number of people, 2.96 T plus 278.649. Woof. Okay, so then what that means is we're going to have to flip that if we wanted to write it in another way and multiply it together. So we can either leave it like this, or we could say that our model is going to be that 171,000 times the number of years since 2000 plus 1,361,000. This is going to get flipped and changed to a multiplication sign. So that's all going to be over 1 plus 18,000 times T times 2.96 times T plus 278 and 649 thousandths. Okay, so there is that model. We can either express it either of those two ways. Now that we have our model or our expression, what we want to do is figure out what is the annual healthcare expenditures per resident in 2010. So using this model, what we can do is, and I would highly recommend typing it into your calculator, just type in this whole thing, but everywhere that we have a T, to figure out what it's going to look like for our healthcare expenditures in 2010. What we're going to have to do is we're going to take these numbers, and everywhere that there's a T, we are going to substitute in the number 10. And the reason why we're going to substitute the number 10 in is because that T represents the number of years since 2000, not the actual year itself. So plus 1361000 all over 1 plus 0.018 times 10 times 2.96 times 10 plus 278 and 649 thousandths. Okay, so we can type in that whole long expression into our calculator, remembering to use our parentheses. So we've got 171,000 times 10 plus 1,361,000. And that whole thing is going to be divided by 1 plus, sorry, this down here is a 1. Sometimes my pluses get squozen in there. 1 plus 18 thousandths times 10 times 2 and 96 hundredths times 10 plus 278 and 649 thousandths. Okay, so now that we have all of that written there, we can hit equals, and it ends up being that the annual, on average, the average annual healthcare expenses in the year 2010, they thought were $8,442.99. Woof, that is a lot of money per resident if you think about that. $8,000. Crazy. So that is how we can use the idea of dividing rational expressions to apply it in the real world. We see that idea all the time when it comes to extrapolation of data and trying to understand what data, how data works and how it will relate to other things. If you have any questions, feel free to reach out, but that is dividing rational expressions.